Imagine a place where time slows, space bends, and even light itself cannot escape. A region so mysterious that it defies human understanding. That's a black hole. These cosmic monsters are born from the death of massive stars, collapsing under their own gravity until they form a point of infinite density. Nothing we know behaves quite like them. They are the ultimate paradoxes of the universe. To truly understand what a black hole is, we must forget everything we think we know about the laws of nature. In normal space, gravity pulls objects toward one another, but near a black hole, that pull becomes unimaginably strong. The closer something gets, the faster it must move to escape, until not even light can reach the speed required. Once past that invisible threshold, it's gone forever. Black holes aren't really holes at all. They're regions of warped space-time. Einstein's theory of general relativity predicted their existence over a century ago, but even he doubted nature could create something so extreme. Today, however, we know they're real. We've seen their fingerprints, the way they twist light, distort time, and consume everything in their path. The fascinating part is that black holes come in many sizes. Some are only a few times the mass of our sun, while others are billions of times heavier, lurking at the centers of galaxies. The difference lies in how they were born, some from dying stars, others from ancient cosmic events that remain unsolved mysteries. But here's where curiosity turns into obsession. If black holes trap everything, including light, how do we even know they exist? The answer lies not in what we see, but in what we don't. Their presence reveals itself through the chaos around them, matter swirling, stars vanishing, and radiation screaming into the void. They are silent monsters, visible only through their destruction. The more scientists study black holes, the stranger they become. They aren't just destroyers. They might also be creators, shaping galaxies and influencing the very structure of the cosmos. It's as if they sit at the heart of everything, orchestrating the universe in silence. And perhaps the most haunting thought of all, black holes might hold the key to understanding reality itself. Somewhere beyond that invisible veil lies a secret about time, space, and existence that humanity has yet to grasp. What if, inside a black hole, the universe rewrites its own rules? These questions are what make black holes irresistible. They're cosmic puzzles, terrifying, beautiful, and essential to understanding who we are in the grand scheme of the universe. The more we learn, the more they challenge everything we believe about reality. But before we dive into the science behind their creation, let's rewind a bit. To a time when even naming these cosmic enigmas was a mystery. After all, how do you name something that devours light itself? The origin of the name black hole and the mystery behind it. The name black hole might seem obvious today, but it was once controversial, even laughed at by scientists. In the 1960s, physicist John Wheeler popularized the term to describe an object that traps everything, including light. Before that, they were known by clumsier names like frozen stars or collapsed objects. Wheeler's phrase captured both their simplicity and terror. The word black refers to the total absence of light. Nothing escapes, nothing shines back. The word hole symbolizes the one-way journey into oblivion. Together they evoke something more poetic than scientific, a cosmic abyss. But there's a hidden brilliance in that simplicity. The name made an abstract concept vivid and unforgettable. What's fascinating is how the term shaped our perception of the universe. Suddenly, black holes weren't just mathematical curiosities. They became characters, dark, mysterious entities devouring worlds and bending time. The name gave life to an idea that once existed only on paper. Some early astronomers actually resisted the term. They argued that it sounded too sensational, too unscientific. But as the evidence mounted, the name stuck, and with it came a wave of cultural fascination. Movies, books, and even music began to reference black holes as symbols of danger and wonder. There's an irony here. The more we learned, the more we realized that the hole isn't really a hole at all. It's a dense, compact object wrapped in its own gravitational prison. Yet, in a way, the metaphor fits perfectly. Once something crosses the boundary, it's as if it falls out of the universe entirely. In many ways, the term black hole mirrors our fear of the unknown. It represents everything humanity can't yet explain, the dark corners of existence that science keeps trying to illuminate. The deeper we look into them, the more questions arise. What's inside them? Do they lead somewhere else? Could they be gateways to another reality? These questions aren't just scientific, they're existential. And that's what makes black holes so captivating. They force us to confront the limits of our understanding. And so, from a name once mocked, the black hole became one of the most powerful symbols in science. It's a reminder that sometimes the universe hides its greatest truths behind the simplest words, and that mystery itself is what keeps us reaching for the stars. How a black hole is born. The stellar collapse. Every black hole begins as a star, but not just any star. Only the most massive ones, many times larger than our sun, have the power to end in such spectacular destruction. As these titans burn through their fuel, they fight a constant battle between gravity pulling inward and nuclear fusion pushing outward. It's a delicate balance that keeps them alive, until one day, the fuel runs out. When fusion ceases, gravity wins. The star's core, no longer supported by the outward pressure of fusion, collapses under its own immense weight. In an instant, the outer layers explode outward in a cataclysm known as a supernova, one of the most powerful events in the universe. For a brief moment, that single star can outshine an entire galaxy. But what's left behind after the explosion is far more fascinating. The core that remains continues collapsing, shrinking smaller and smaller until it reaches a point where matter itself can no longer exist in its normal form. This is the birth of a singularity, a point of infinite density, where all known laws of physics break down. Imagine something as massive as the sun compressed into an object smaller than a city. The gravity becomes so extreme that it warps space and time around it, bending the universe like fabric under tremendous pressure. The result is a region from which nothing, not even light, can escape. The black hole. Some stars become neutron stars instead, stopping just short of the black hole stage. But if the collapsing mass exceeds roughly 3 times the mass of the sun, nothing can stop gravity's relentless pull. The collapse continues endlessly, and the event horizon, the boundary of no return, forms. From that moment, the black hole is born. It's invisible, silent, and yet immensely powerful. It doesn't emit light, but reveals its existence through the chaos it creates. Swirling disks of gas, beams of energy, and the violent dance of nearby stars caught in its gravitational trap. This process might sound like destruction, but it's also creation. The explosion that births a black hole scatters heavy elements into space, the same elements that later form planets, oceans, and even life. In a poetic twist, the death of one star may be the beginning of countless worlds. So when we look at the night sky and see stars twinkling in the distance, some of them are ticking clocks. Future black holes waiting to be born. And when they finally collapse, they leave behind the most mysterious objects in the universe. But what makes black holes truly terrifying isn't just how they're born, it's what they do. Because once gravity takes control, even light, the fastest thing in existence, can't get away. The gravity's so strong that even light can't escape. Gravity is the most familiar yet misunderstood force in the universe. It keeps our feet on the ground and the planets in orbit, but near a black hole, gravity becomes something alien, a force so intense that it twists the very fabric of reality. To escape Earth's gravity, a rocket must travel at about 11 kilometers per second. Near a black hole, the escape velocity exceeds the speed of light itself. And since nothing can move faster than light, nothing can ever leave. That's what makes black holes truly black. They are cosmic prisons from which no signal, no information, and no ray of light can return. Once something crosses that invisible threshold, known as the event horizon, it's lost to the outside universe forever. Einstein's equations predicted this long before anyone believed it was possible. His general theory of relativity showed that mass can warp space and time, curving it around itself. A black hole is simply the ultimate example of this curvature. a place where space folds so deeply that it becomes a one-way tunnel inward. To visualize it, imagine placing a heavy ball on a rubber sheet. The sheet bends, and smaller balls roll toward it. Now imagine that ball getting infinitely heavy. The sheet would tear and everything nearby would be pulled in. That's what a black hole does to space-time, except on a cosmic scale. Near a black hole, time itself slows down. If you were to watch someone falling in, you'd see them freeze at the edge of the event horizon, never quite disappearing. To them, though, time continues normally, until they are stretched, crushed, and ultimately absorbed into the darkness. What's mind-blowing is that, while we can't see what happens inside, we can observe the effects outside. Matter swirling around the black hole heats up to millions of degrees, emitting X-rays and gamma rays detectable by telescopes. These cosmic signatures are the footprints of the invisible. Black holes, therefore, aren't just voids, they are engines of immense energy. Paradoxically, the darkest places in the universe are also some of the brightest when seen from afar, thanks to the furious radiation produced by matter just before it's consumed. Scientists have even detected black holes merging, releasing gravitational waves that ripple across space-time, literal vibrations of the universe's fabric. These waves were first recorded in 2015, confirming Einstein's century-old prediction and giving humanity a new way to hear the cosmos. It's poetic, isn't it? The very force that pulls everything inward, gravity, also sends waves outward, allowing us to sense the universe's most violent events. But as we approach the boundary of the event horizon, things only get stranger. The event horizon. The point of no return. Every black hole is surrounded by an invisible boundary. The event horizon, a line that divides the universe into two realms, what can still escape and what never will. Cross that boundary, and no signal, no light, no information can return. It's the ultimate cosmic trapdoor, where even time seems to hesitate before vanishing. The event horizon isn't a physical surface. You wouldn't crash into it or feel a sudden impact. Instead, you'd simply pass through, unaware that you've crossed the most unforgiving threshold in the universe. It's an illusion, a border defined not by matter, but by the laws of physics themselves. At this boundary, space and time are so warped that all paths lead inward. Once something crosses, all possible futures point toward the singularity. To escape would require moving faster than light, and nature forbids that. This is where reality becomes a one-way journey. If you could hover just outside the event horizon, you'd see bizarre effects. Light from distant stars would bend and distort, creating a glowing halo around the black hole, an optical illusion caused by gravity bending space itself. This glowing edge, known as the photon sphere, is one of the most mesmerizing sights in the cosmos. From your perspective, time would flow normally. But to an outside observer watching you, it would appear as if you were slowing down, your movements stretching infinitely as you approach the horizon. Eventually, you'd seem to freeze in place, a ghost image forever trapped on the edge of darkness. This time, distortion isn't fiction, it's a real consequence of Einstein's relativity. Time and space are intertwined, and gravity can warp both. Near a black hole, the warping becomes so extreme that time itself almost stops from an outside point of view. The event horizon is the ultimate symbol of mystery, a place beyond which our laws of physics can't describe what happens. It's the edge of knowledge, where human understanding simply breaks apart, just like matter falling inside. Astronomers often compare it to a cosmic curtain. We can see the play happening just before the drop, the swirling light, the radiation, the chaos, but never what's behind it. It's both beautiful and terrifying, the universe's way of saying, no further. And yet, our curiosity refuses to stop there. If we can't look inside directly, perhaps we can imagine what it would feel like to cross that boundary ourselves. So, what would happen if you fell into a black hole? What would happen if you fell into a black hole? Imagine floating through the silent void, staring into a black hole. Its darkness stretches before you, like a wound in the fabric of space. There's no sound, no sensation, just an irresistible pull. You know that crossing the horizon means no return, but your curiosity wins. You drift closer, and the real horror begins. As you approach, gravity's pull becomes stronger on your feet than on your head. The difference in force grows exponentially, stretching your body into a long, thin thread. This process, called spaghettification, is as terrifying as it sounds. You wouldn't feel pain immediately. You'd simply elongate until your atoms tear apart. From your point of view, you'd continue falling normally. But to someone watching from afar, you'd appear frozen at the edge, slowly fading as light from your body redshifts into invisibility. They'd never see you cross the event horizon, only vanish into darkness. Time itself would seem to stop for you. The deeper you fall, the stranger physics becomes. Space starts to curve inward, directions lose meaning, and time may even flip roles with space. What once was forward now points toward the singularity, the ultimate destination of everything that falls inside. If the black hole is small, your end would come quickly. You'd be crushed before you could comprehend it. But in a supermassive black hole, like the one at the center of our galaxy, the experience might be surprisingly gentle at first. You could pass the horizon without noticing. Gravity's pull spreads so evenly that you'd feel nothing, at least for a while. Inside, no one truly knows what happens. Some theories suggest the laws of physics collapse completely. Others imagine you'd encounter a bridge, a wormhole, connecting to another universe. But there's no way to test it. It's a realm forever hidden from our reach. Your final moments, according to physics, would be timeless. From your perspective, you'd reach the singularity in seconds. From the outside, you'd appear frozen forever at the edge, a paradox born from relativity. You'd exist and not exist at the same time, trapped between two definitions of reality. And then, nothing. The singularity waits, a point of infinite density where all known concepts of space, time, and matter disintegrate. You'd become part of the black hole's mass, your identity erased but your essence contributing to the most mysterious object in the cosmos. So while falling into a black hole would mean your end, it's also an entry into something larger, a place where the universe folds in on itself and everything we know loses meaning. It's terrifying, yes, but also profoundly beautiful. Spaghettification, the most bizarre death in the universe. If there's a way to die that defies imagination, it happens near a black hole. Scientists call it spaghettification, and the name is both strange and horrifyingly accurate. It's what happens when gravity pulls on you so unevenly that your body stretches thinner and thinner, until you're literally torn apart molecule by molecule. The force behind this nightmare is called a tidal gradient. It's the difference in gravitational pull between 2 points on your body, say, your head and your feet. Near a black hole, that difference becomes unimaginably vast. Your feet, being closer, are pulled far more strongly than your head, creating a stretching effect that no living thing could survive. At first, it might happen slowly, almost imperceptibly. But as you get closer, the pull increases exponentially. Your body elongates into a long, thin strand, atoms separating, electrons ripped away, the very structure of matter unraveling. You don't burn, you don't explode. You simply cease to be as a solid form. What makes it truly eerie is that from your perspective, it might feel completely normal. Relativity dictates that you wouldn't notice anything particularly special as you cross the event horizon. Yet from the outside, an observer would see you stretched, dimmed, and then vanished, a ghost disappearing into silence. This process doesn't just happen to humans. Stars, gas clouds, even entire planets can be spaghettified. When a star strays too close to a black hole, it gets shredded into a luminous stream of plasma, swirling into a brilliant accretion disk before being consumed entirely. It's death turned into a light show. In fact, telescopes have observed this very phenomenon. In 2019, astronomers witnessed a star being torn apart by a supermassive black hole in another galaxy. A tidal disruption event so powerful it briefly outshone all the stars around it. It was spaghettification on a cosmic scale. Ironically, this violent process helps us understand black holes better. The light and radiation emitted during spaghettification give scientists clues about the black hole's mass, spin, and energy. In a way, every act of destruction reveals more about the nature of the destroyer. So while it's a gruesome fate, spaghettification also serves as a window into one of the universe's greatest mysteries. The deaths of stars feed our understanding of cosmic life. It's yet another paradox of the universe that the most violent processes can lead to the brightest revelations. And as haunting as it sounds, the story doesn't end with destruction. Because what happens around black holes doesn't just erase, it also creates. Black holes are not the villains of the cosmos. They're its architects. The role of black holes in shaping galaxies. It might seem counterintuitive. How can something that destroys everything around it also create the structures of the universe? Yet, black holes do exactly that. At the heart of nearly every galaxy lies a supermassive black hole, and it plays a crucial role in shaping the stars, gas, and systems that orbit it. These cosmic giants act like galactic anchors. Their immense gravity helps bind galaxies together, influencing how stars form and how they move. Without black holes, the elegant spirals and clusters we see in the night sky might never have taken shape. They are both the heart and the heartbeat of galaxies. When black holes feed, devouring gas, dust, and stars, they release staggering amounts of energy. Jets of particles shoot out from their poles at nearly the speed of light, stretching across thousands of light years. These relativistic jets can heat nearby gas and even stop new stars from forming, regulating the galaxy's growth. In a sense, black holes act like cosmic thermostats. They control the balance between creation and destruction, between chaos and order. Too much feeding, and star formation halts. Too little, and galaxies collapse inward. Somehow nature finds equilibrium, and black holes are the mechanism that maintains it. The black hole at the center of our own galaxy, Sagittarius A, is a perfect example. Though currently quiet, it once flared brightly, influencing the Milky Way's structure. Ancient traces of its activity, vast bubbles of radiation, still glow faintly above and below the galactic plane, silent witnesses to its power. Without these cosmic engines, galaxies might be unstable, chaotic clouds of stars with no structure. Instead, black holes bring order through destruction, symmetry through violence. It's a paradox that lies at the heart of the cosmos, creation and annihilation, intertwined forever. Even more fascinating is that the mass of a galaxy seems directly linked to the mass of its central black hole. It's as if galaxies and black holes evolved together, growing in tandem, each shaping the destiny of the other in a cosmic partnership spanning billions of years. When we look up at the night sky, every shining galaxy tells the same story. At its center, hidden behind light years of dust, a silent colossus spins, invisible yet essential. It's not a monster. It's the architect of everything around it. And yet, for all their influence, we've only just begun to see them clearly. The first photograph of a black hole changed everything, turning theory into reality and mystery into awe. Supermassive black holes, the giants at the center of the cosmos. At the center of nearly every galaxy, there lies a colossus, a black hole millions or even billions of times the mass of the sun. These are the supermassive black holes, the gravitational hearts of the universe. Silent, ancient, and invisible, they govern the dance of stars and the evolution of galaxies themselves. Our own Milky Way hides one such giant, Sagittarius A. Though dormant now, it once blazed fiercely, shaping the structure of our galaxy. Astronomers have observed stars orbiting an unseen point near its center, moving so fast that only a supermassive black hole could explain it. What we cannot see still holds everything together. But how do such cosmic monsters form? That remains one of astronomy's greatest mysteries. Some theories suggest they were born from the first generation of stars, ancient behemoths that collapsed in the early universe. Others believe smaller black holes merged over billions of years, growing until they became galactic titans. To grasp their scale is to stretch the limits of imagination. The black hole at the center of M87, for example, has a mass equivalent to 6.5 billion suns. Its event horizon, the boundary of no return, could swallow our entire solar system and still have room to spare. Around it, space itself swirls like a vast whirlpool of fire and gravity. Despite their destructive reputation, supermassive black holes aren't mere cosmic predators. They are also creators. The energy released as matter spirals into them can ignite galaxies, drive star formation, and shape cosmic evolution. They regulate life on a galactic scale, the ultimate paradox of creation through destruction. Incredibly, these black holes may also act as cosmic engines. When they feed, they can hurl out jets of plasma that stretch across hundreds of thousands of light years. These jets influence everything they touch, compressing gas clouds, seeding stars, and sculpting galaxies with invisible hands. Even when they sleep, their presence defines the rhythm of the cosmos. Stars orbit them, matter bows to them, and light bends around them. It's as if the entire galaxy exists to serve them, loyal subjects to a king made of darkness. And yet, despite their dominance, we had never seen one directly. For decades, they existed only in equations, theories, and imagination, ghosts of gravity, invisible yet undeniable. Until one historic moment changed everything. In 2019, humanity finally gazed into the abyss, and for the first time, the abyss gazed back. The historic image of M87, photographing the impossible. April 10th, 2019, a date that redefined what we mean by seeing the unseen. On that day, scientists revealed the first ever image of a black hole, a glowing orange ring surrounding a shadow of infinite darkness. It wasn't just a photograph, it was proof that our universe's most terrifying idea was real. The black hole in question lies at the center of the galaxy M87, over 55 million light-years away. Capturing its image was an achievement that defied imagination. No single telescope could ever see something so distant, so small, and so dark. So scientists combined the power of 8 telescopes around the world, creating one planet-sized eye, the Event Horizon Telescope. For years, these telescopes synchronized perfectly, collecting radio waves emitted by the hot gas swirling near the event horizon. Then came the true challenge: assembling petabytes of data from across the globe and stitching it together, piece by piece, to reveal the first glimpse of a black hole's silhouette. The result stunned the world: a blurred, fiery ring surrounding a circular void. That dark center wasn't an object, but the shadow of the event horizon, the point where light itself vanishes. The ring of light was matter heated to billions of degrees as it circled the black hole's maw, moments before its destruction. For scientists, that image wasn't just confirmation, it was vindication. Decades of equations, predictions, and skepticism had led to this one moment. Einstein's theory of relativity had once again proven true, down to the smallest detail of the ring's curve. But for the rest of us, it was something deeper. That image felt like staring into eternity. A human eye, built through technology, persistence, and curiosity, had looked straight into one of nature's greatest mysteries. It was both humbling and empowering, proof that even the darkest parts of the universe can be revealed through human ingenuity. The project wasn't just scientific, it was poetic. Thousands of people from dozens of countries worked together, across cultures and continents, to photograph something that devours light itself. In a sense, it was humanity's triumph over cosmic darkness. And yet, that single glowing ring raised more questions than it answered. How does matter behave on that razor's edge between existence and oblivion? What happens inside? Could the laws of physics themselves break down beyond that dark horizon? As the image of M87's black hole spread across the world, one thing became clear. We weren't looking at the end of knowledge. We were standing at its edge. The photograph didn't close a chapter in science. It opened one.
Stephen Hawking and the radiation that defies physics. For decades, scientists believed that black holes were the ultimate endpoints of the universe, eternal prisons from which nothing, not even light, could escape. But then came Stephen Hawking, the man who dared to question the unbreakable. His idea would change our understanding of black holes forever. In 1974, Hawking combined two pillars of science that had long resisted one another: quantum mechanics and general relativity.
What he discovered was astonishing. Black holes, he said, weren't completely black after all. They could actually emit energy, a faint glow now known as Hawking radiation. This revelation turned physics upside down. If black holes could lose energy, they could also lose mass, meaning they wouldn't last forever. Over unimaginable spans of time, they could slowly evaporate, shrinking until they vanish entirely. Even the most massive ones would eventually fade into nothingness. But the real shock wasn't their death. It was what it meant for information. Quantum mechanics insists that information can never be destroyed. Yet, if a black hole evaporates completely, where does that information go? This question became known as the information paradox, one of the greatest mysteries in modern physics. Hawking's discovery didn't just challenge existing theories, it ignited a scientific revolution. It forced physicists to rethink the nature of space, time, and reality itself. Could information somehow escape the black hole, hidden within the radiation? Or does the universe rewrite its own rules at the edge of the event horizon? Even today, no one knows the full answer. String theory, quantum gravity, and holographic models all try to reconcile the paradox. But Hawking's insight remains the spark that drives the quest. It's as if he cracked open the door to a new layer of the universe, one where physics itself begins to blur. Beyond science, Hawking's discovery carried something deeper, a message about curiosity and courage. Despite being trapped in his own body by illness, he ventured mentally into places no one else could. He explored the darkest corners of the cosmos and found light where none should exist. Hawking radiation reminds us that even the universe's most terrifying objects are not absolute. Nothing lasts forever, not even black holes. In their slow fading, we find the poetry of impermanence, the cosmos itself whispering that everything, no matter how powerful, eventually changes form. And so, as black holes evaporate across eons, they leave behind more than mystery. They leave a challenge to keep seeking, questioning, and expanding our understanding of what's possible. Because if even black holes can shine, what limits could possibly bind the human mind? Wormholes and the possibility of time travel. If black holes mark the end of everything, could they also be the beginning of something else? Some physicists believe that within their dark hearts might lie passages, tunnels through space and time known as wormholes. They are the universe's most tantalizing what if, where science meets imagination. A wormhole, in theory, is a bridge connecting two distant points in the cosmos. Imagine folding a sheet of paper and punching a hole through it. The 2 points meet instantly. That's how a wormhole could work, bending the geometry of space-time to make shortcuts across vast distances. The concept dates back to Einstein and Nathan Rosen, who proposed the Einstein-Rosen bridge, a mathematical structure that could, in theory, connect two black holes. Later, physicist Kip Thorne and others expanded the idea, exploring whether such tunnels could actually exist or even allow time travel. But nature isn't easily tamed. Wormholes, if real, would be inherently unstable. The intense gravity inside would cause them to collapse instantly. To keep one open, you'd need a form of exotic matter, material with negative energy density, something that defies our current understanding of physics. Still, the idea fascinates scientists and dreamers alike. Wormholes appear in countless works of science fiction because they represent the ultimate escape, a way to transcend distance, time, and mortality itself. They speak to our deepest desire, to go beyond the limits of the possible. What's more, some theories suggest that black holes and wormholes might actually be connected. The singularity at a black hole's core could serve as a gateway, linking different regions of the universe, or even different universes altogether. If true, every black hole could be a door. The question then becomes, where does it lead? To another galaxy? Another dimension? Or perhaps back in time, a loop in the cosmic fabric where cause and effect intertwine. Each possibility is stranger than the last, yet grounded in real physics. Time travel itself, though theoretically possible through wormholes, brings paradoxes. Could you meet your past self? Change history? Or would the universe find a way to preserve consistency no matter what? Even in equations, time refuses to give up its secrets easily. For now, wormholes remain mathematical ghosts, beautiful, elusive, and unproven. But their very existence in our theories shows how far the human mind can stretch. From black holes that devour light to wormholes that could bend it, we are explorers of the impossible. Because in the end, wormholes are not just about escaping space. They are about expanding imagination. They remind us that the universe may be far stranger and far more connected than we ever dared to believe. What's inside a black hole? Theories and paradoxes. Imagine crossing the event horizon and falling into absolute darkness. What lies beyond that point is one of the greatest mysteries in science, and perhaps something the human mind will never truly comprehend. Inside a black hole, the known laws of physics collapse. Reality as we understand it simply stops working. At the center, theory predicts a singularity, an infinitely small, infinitely dense point where matter is crushed beyond recognition. It's a region where gravity becomes infinite and space-time curves in on itself. But here's the problem. Infinities don't exist in nature. They're signs that our equations have reached their breaking point. Einstein's general relativity can describe the outside of a black hole perfectly, but inside, it fails. Quantum mechanics, which governs the microscopic world, offers no clear answers either. To truly understand the singularity, we need a theory of quantum gravity, something that unites the two great frameworks of physics into one. Some scientists believe the singularity might not even exist in the traditional sense. Instead, matter could be compressed into a tiny but finite region, or the laws of physics could warp to create something entirely new, perhaps even a bridge to another universe. Others suggest that the center could be a bounce point, where matter collapses and then explodes outward elsewhere. Then there's the information paradox, one of the most haunting puzzles in science. If black holes destroy everything, including information, that would break one of the fundamental rules of quantum mechanics, that information cannot be lost. But if it escapes somehow, how does it do so from a place where nothing escapes? Some theories propose that the information is preserved on the surface of the event horizon itself, encoded in the subtle fluctuations of Hawking radiation. This is the holographic principle, suggesting that everything inside a black hole might actually be described by data imprinted on its boundary. It's as if reality itself were a cosmic hologram. Others go further, speculating that black holes could act as gateways, not just to other places, but to other universes entirely. If so, every black hole might be a portal, connecting countless realities within a vast, multidimensional cosmos. Each one could be a seed of creation, giving birth to new universes beyond our own. But these are theories, not certainties. The truth is, we don't know what lies inside, and maybe we never will. The laws of physics protect that secret behind a curtain no light can pierce. The inside of a black hole is, quite literally, the ultimate unknown. Perhaps that's what makes them so mesmerizing. They represent the limit of human knowledge, the place where curiosity meets the infinite. In the silence beyond the horizon, the universe keeps its deepest secret, waiting for us to evolve enough to understand it. And as if that mystery weren't profound enough, black holes themselves are not eternal. Even these titans of darkness have a lifespan, and astonishingly, they too must die. The death of a black hole. Even darkness fades. It may sound impossible. How can something that swallows light itself ever die? Yet according to Stephen Hawking's theory, black holes are not everlasting. Over eons upon eons, they slowly evaporate, losing mass through the faint whisper of Hawking radiation until nothing remains. At first, this radiation is unimaginably weak. For massive black holes, it takes longer than the age of the universe for the process to matter. But as they lose energy, the radiation increases. The black hole grows smaller, hotter, and more unstable, like a cosmic ember fading in the darkness of eternity. Eventually, after trillions of years, it reaches a critical point. The black hole becomes tiny, its energy erupting in one final burst, a brilliant flash that releases everything it had left into the void. the last echo of a phenomenon that once ruled galaxies, the death of darkness itself. This is more than science. It's cosmic poetry. The very entities that embody destruction end their existence through creation, returning energy to the universe. Even in their death, black holes feed the cosmos, closing one loop only to open another. And here lies the profound beauty of it. Nothing lasts forever, not even the universe's darkest hearts. Stars are born and die, galaxies collide and vanish, even the void itself evolves. Change is the universe's only constant, and black holes, the symbols of eternity, are no exception. In their long, slow fading, black holes remind us of something deeply human, that even the most powerful things must one day transform, that endings are not failures but transitions, from one form of existence to another, from order to chaos, from energy to light. When the last black hole evaporates, countless trillions of years from now, it will mark the final act of the cosmic story we know. A universe once bright and full will fall silent, not in tragedy, but in peace. The final whisper of radiation will ripple through the void like a heartbeat fading into stillness. But perhaps that's not the end. Maybe from that quiet, something new will emerge. A new universe, a new beginning. Because if the cosmos has taught us anything, it's that every ending hides the seed of creation. And so, even darkness must die, but its death may one day give birth to new light. What if the entire universe is inside a black hole? What if the greatest mystery of all is not what's inside black holes, but the possibility that we are? It's a question that sounds like science fiction, yet it's a theory some physicists take seriously, that our entire universe could exist within the event horizon of another black hole, a cosmos born from collapse, not creation. In this idea, the Big Bang wasn't the beginning of everything, but rather the birth of a new universe inside a parent one. When a massive star collapses into a black hole, its singularity could explode outward, not in its own space, but within a newly formed bubble of reality. From the outside, the star dies. From the inside, a universe is born. This theory elegantly connects creation and destruction. Every black hole could be a cosmic womb, giving rise to new universes beyond its event horizon. In turn, our own universe, vast and ancient, might simply be one of countless others, each nested within another like Russian dolls of infinity. If that's true, then everything we know, galaxies, stars, life, and thought, exists inside a black hole's event horizon, expanding within the space created by a singularity long ago. The laws of physics, the speed of light, the passage of time, all might be the byproducts of that original cosmic collapse. It's a humbling idea. It suggests that our universe isn't the whole story, just one page in an endless book written in gravity and time. And somewhere beyond our reach, perhaps beyond the blackness of other holes, lie other universes with their own stars, histories, and questions. If every black hole births a new universe, then black holes are not destroyers, they're creators. They recycle matter, energy, and information, ensuring that nothing in existence is ever truly lost. The universe, then, is not a place of endings, but of continuous transformation. And maybe that's the secret. That creation and destruction are the same force, viewed from different sides of the event horizon. From our perspective, a star's death is tragic. But from another universe's perspective, it's the beginning of everything. The boundary between life and death, light and dark, is only perception. Even the ultimate questions, where we came from, where we're going, may not have single answers. If the universe is infinite, looping through collapse and rebirth, then perhaps existence itself is eternal. The cosmos doesn't end, it changes shape, forever folding and unfolding upon itself. So, when we stare into a black hole, perhaps we're not just looking at the end of matter, but at the beginning of creation. The shadow we see isn't just darkness, it's the mirror of eternity, reflecting the endless cycle of life and death that defines the universe. And in that reflection, maybe we see ourselves, small, fragile, and fleeting, yet made of the same fabric as stars and black holes alike. Because the greatest truth of all might be this: we are not merely observers of the cosmos. We are the cosmos looking back at itself.